Hello, I would like to give you hopefully an easily understood explanation about how we get to the geometric sequence and series formulas. They look a little bit more complicated than the arithmetic sequence and series formulas, but hopefully after you watch this, you'll kind of understand where they come from, and once you get used to them, they'll be just as easy as the arithmetic sequences and series. Now, I just want to review how we figured out the arithmetic sequences and series formulas, especially the series, which is the sum. So remember this formula for arithmetic series. It would be how you sum up the area of those cutout triangles that we made. Remember this formula? Okay, and the way we figured that out, if you remember, is I gave you those cutouts. And then I said, what's an easy way to figure out the area of this cutout if you know this height and this height, which happen to be U1 and UN? How do you figure out the area? And after your exploration or your investigation, what you figured out was that if you cut it in a certain place, and then you took this piece here, and then you fit it here, that you would end up with a rectangle about this size. And once you have it in that rectangle form, then you can figure out the area of this rectangle just by using length times width. And of course, the length times width here is the width would be n, and the height here you can figure out from u1 and un. You figured out that it was the average of u1 and un, right? That this height of this rectangle would be exactly in the middle of u1 and un. And so if you multiply this height times this width together, you get the arithmetic sequence and series formula. Okay, so we're going to do something similar to that, a little bit more complicated, but I think you can understand it, for geometric sequence and series. Okay, and so to do that, I'm going to show you your investigation again, because there's some numbers from the investigation that I want you to remember. And I think that you already remember these numbers from doing the investigation, but I want you to kind of memorize these numbers so that when they come out later, they're not a surprise. Okay, so first of all, remember in number 2, I asked you what operation do you do to go from one day's running distance to the others? And you said, I multiply by 1.1. Okay, actually this 1.1 that you multiply by is similar to the d value that you used in arithmetic sequence and series, except for this one is called the r, which is the common ratio. If you remember in arithmetic sequence and series, it was called common difference. In this case, it's called common ratio, r. Okay, so 1.1 is the common ratio. The other things that I want you to remember are here at the bottom in the table. I want you to remember that on the first day we ran 2 kilometers, or Javier ran 2 kilometers. And the other numbers I want you to remember is on the 18th day he reached slightly over 10 kilometers, it was 10.11 kilometers. And this number we never calculated, but it's useful for the derivation of the formula, which is on the 19th day he would have ran 11.12, which is just 10.11 times 1.1. Okay, so I just want you to remember these yellow numbers. Okay, so I want you to remember 19. On the 19th day he would have run 11.12. On the 18th day he ran 10.11, and on the first day he ran 2. You might remember some of these numbers in between, but you don't have to. Okay, and what are we trying to figure out? We're trying to figure out an easy way to figure out, without the calculator, that the total of all the distances he ran from day 1 to day 18 is 91.2, which we figured out with the calculator pretty easily. But without the calculator, how could we also figure this out easily using a trick similar to one from arithmetic sequence and series? Okay, so let's go back to this sheet. Okay, so the first thing I'm going to do is I'm going to draw a picture which is similar to this one I'm showing you on the left. What is this picture? This is a picture similar to the one that we had for cutouts for arithmetic sequence series. It's showing you with bars the distances that the person ran from day 1 to day 18. So you can see that in this blue bar graph, we can see that the first bar is day 1, the last bar is day 18, and in between day 1 and day 18, he ran distances ranging from 2 kilometers on the first day. If you look on the graph, you can see that it says 2 kilometers for the first day. And on the very last day, you can see it's slightly over 10. Actually, it's 10.11. Okay? Now I'm going to draw a crude representation of this graph right here. It's not going to look as nice, but you'll get the idea. Okay? So what you see there looks kind of like this, right? It's kind of triangular, but you can see that it's curved because it's like the slope increases as it goes to the right, right? And then, as you can see, behind this blue graph, I have a red graph, which is slightly larger. The red graph is slightly larger. Okay? And if we look at key numbers for the red graph and the blue graph, we can see them here, and I'm going to write them here to the side. Okay? First of all, the width of this graph is 18, right? You can see there it goes from 1 through 18. And the first height here is 2, as you can see, right? And the last height is 10.109, which is the same thing pretty much as 10.11. Okay? Now these should look familiar because these are numbers I asked you to memorize. The first day he ran 2 kilometers. The last day, the 18th day, he ran 10.11 kilometers, right? So this is 18 days, all right? Now this red graph, and you're not going to understand why we did this yet, but at the end you'll see why. The red graph is the same as the blue graph, except for we include the 19th day, which we didn't even do in the investigation. But remember, you memorized that the 19th day he would have run 11.12. It's just 10.11 times 1.1. Okay, so the height of the last bar of the red graph is 11.12. And the first day, of course, is 2, just like the first day of the blue graph. And now what the width of the red graph is slightly wider than the blue graph, right? It's 19 days instead of 18. Now you don't have to understand why I did this so far, but I want you to understand everything I did so far. The blue graph is the same as what we did on the investigation. We calculated on the first day he ran 2 kilometers, on the last day, the 18th day, he ran 10.11. So this is a graphical representation of what we did on the investigation. And then this red graph is just one extra day. It also has the 19th day. Okay? Okay, there's another thing that we need to do here. And the other thing is, we want to make a formula for UN. Okay? So remember, UN is how you find the term. And that wasn't so difficult for geometric sequence and series. Once we started working on the investigation, you guys figured that out right away. The first day, U1 was 2. The second day was 2 times 10% more, which was 1.1. You figured that out after a few tries. So the second day, he ran 2.2. On the third day, you take 2 times 1.1, and then you multiply it again times 1.1. So that's actually 2 times 1.1 squared equals, and the result was 2.42. I didn't ask you to memorize that, but maybe you remember that. Okay? Now, you'll notice a pattern here. If we say that this is 1.1 to the first, you can see that to find u to the n, you would take 2 times 1.1 times n minus 1. You see that this number is always 1 bigger than this number. This number is 1 bigger than this number. Okay, and that's how it continues. So actually, you put n here and you put n minus 1 here. Okay? So now let's replace these with variables. So u1 is actually equal to 2, which happens to be u1, times 1.1, which remember from the investigation, 1.1 is actually r, and then n minus 1. And so we just found the formula to find any term of the sequence. It's u1 times r to the n minus 1. Okay, and in the case of the investigation, u1 was 2 and r was 1.1, but in other problems, it's not going to be the same. So we need this expression later. Okay, now we have the blue curve and the red curve, and we're going to figure out the area of the blue curve. And the first thing we do to do that is we say that the area of the red curve is equal to the area of the red curve. Okay? And then we are going to write the area of a red curve in two different ways. Okay? And we're going to use the blue curve to write the area. Now, this is why I have this manipulative here on the left. Okay? So if you see the blue curve and the red curve, you can see that they're very similarly shaped. Not only are they similarly shaped, if I put the blue curve, if I put it on the x-axis also, and I slide it all the way to the left, you can see that it is exactly the same as the first 18 bars of the red curve. So it covers up the red curve perfectly, except for the last bar. So the last bar is still uncovered. So how could I express the area of the red curve using the blue curve? Well, the first thing I would say is, well, it's equal to the blue curve, which is, let's see, S18, right? That's the name we gave to the blue curve, plus the last row, the last column, the last bar of the red curve, which we know is 11.12. Okay? So we'll put 11.12 there. What about the other side? How are we going to write it now? Differently, using the blue curve still. Well, the other thing about the blue curve is, if I multiply the whole blue curve by 1.1, make it 10% higher. You see, I'm multiplying by 1.1, it's getting 10% higher. Every single bar here is getting 10% higher. So you can see that the bar, the first bar, which is 2, is now 2.2. See, 2, 2.2. Now look at the last bar. It's 10.109. When I multiply it times 1.1, the last bar becomes 11.12, which is the height of the last bar of the red curve. So if I take the blue curve and I multiply it times 1.1, it becomes as high as the red curve. So I'm going to slide it over to match the red curve again. Oh, but look what happens. Remember that the first bar was 2 and it went up to 2.2, but now the first bar of the red graph is uncovered. Okay? So, but now I can express the area of the red curve as the blue curve times 1.1, and then this little part that's uncovered, which is 2, right? Because the first bar is 2. See? Not times 1.1, times 1.1. So you see it matches it perfectly when we multiply the blue curve by 1.1. Okay, so now we're going to rewrite it again. We're going to put S18. Oops. Okay, we're going to put 1.1 times S18, right? And the red part that is still uncovered is 2, right? So 2 is the first bar that was uncovered here. 11.12 was the 19th bar, which was uncovered here. And in this case, we have S18 times 1.1, and here we just have S18 by itself. So those are two ways of expressing S19 using S18. S18 is the blue curve, S19 is the red curve, the area, right? Okay, now that we have this, do you see how we only have one variable and everything else is known? So we can easily find what the value of S18 is with algebra. Okay, and like I always tell you, it's better if you write every single step down, which I'm going to do here. I'm going to subtract S18 from both sides. Okay, and then I'm going to subtract 2 from both sides. By doing that, I'm going to get, let's see, 1.1 times S18 minus S18 equals, and I'm going to have 11.12 minus 2. Okay? Now, I don't want you to subtract everything out. What I want you to do now is I want you to replace these numbers with variables. Okay? First thing we're going to do is we're going to simplify this part. We're going to have, instead of having S18 separated here, we're going to factor out S18 and we're going to get 1.1 minus 1. Because if you factor out S18, you get 1.1 minus 1. Okay? And then on this side, you keep 11.12 minus 2. Now that we factored out S18, we can divide both sides by 1.1 divided by 1. Or 1.1 minus 1. Okay? And so now what we have is, we'll just use red. We have S18 equals 11.12 minus 2 over 1.1 minus 1. Okay? Now, if you went ahead and did this subtraction and division, you would get 91.2, which is the area of S18. We found that the hard way. This is the easy way. Now, but what we want to do is we want to find the formula, the general formula, which allows you to figure this out for any problem. Okay? And to do that, all we need to do is remember what each of these numbers was. Remember, 11.12 is equal to S19, right? Remember that 2 is equal to U1. Remember that 1.1 is equal to R. And 1 is just 1. Okay? So we're going to replace all these things with what they represent. So we have S18, I'm sorry, I made a mistake here. It's not S19 here. It's U19, right? So U19, this is U1, and this is R minus 1. And we're almost done. The only thing we need to do now is remember that U19 is equal to U1 times R to the 18. Do you remember that? Okay, so let's replace that. That's what we got up here, remember? Right there? Okay, so now we're going to replace it. We're going to put U1 R18 minus U over R minus 1, and that's equal to S18. Now there's one more substitution we're going to do. Remember that 18 is equal to the n value. It's the last bar. So we're going to replace that. Sn equals to U1 R to the n minus U1. Okay? And on the bottom we have R minus 1. And if we want to, we can factor out the U1 so that instead of the way it is, we have this. Okay? And then we have just derived the formula using this trick that the blue curve fits two ways the red curve. It fits here on the leftmost position, and it also fits the rightmost position if you multiply by 1.1. So using that trick, we've just found an easy way to figure out what the sum of all these bars is. And that is if you know the first bar height, and you know the factor, 1.1, and you know how many days, 18. You just plug in all the numbers and you calculate it out, you'll get 91.2. And you could probably even do this calculation without a calculator. Okay? That's how you figure out the geometric sum formula or understand the geometric formula, sum formula, where it came from.